Good morning, class. Today we'll be looking at question 6 from one of the P sets taken from Chem 30. And the basic premise of this question is that we start out with our dienophile labeled molecule A, and then we add in two equivalents of a Lewis acid, which in this case is diethyl aluminum chloride, and we end up with a molecule B and a mystery byproduct, which we will have to identify, which is very exciting. And we'll also need to explain the purpose of using two equivalents of Lewis acid. Beyond that, we also have to explain the impact of Lewis acid activation on both the electronic and conformational structure of the dienophile in a Diels-Alder reaction. Okay, so how should we approach this problem? Where do we even start? Well, for me, I usually like to redraw the molecule so I get a better sense of what's going on and just model what's going on in this reaction sequence. So we can start by seeing what happens to this molecule if we add in just one equivalent of our Lewis acid. And while we are drawing our Lewis acid, we might even wonder what the function of a Lewis acid is. Well, remember how Lewis acids facilitate reactions by lowering the LUMO of the reactant so that the starting material will be more reactive towards a nucleophile. In this case, our reactant is a dienophile, and this complexation of the oxygen's lone pair with the aluminum, which is Lewis acidic, bears positive charge, would mean that the LUMO of this dienophile would be lowered. And we know that when the LUMO of dienophiles are lowered, they would undergo faster Diels-Alder reactions of dienes. I mean, we have to think about why we even need electron withdrawing groups on an alkene in the first place such that a Diels-Alder reaction can even occur. It's to lower that LUMO of the alkene so that you can actually have a viable Diels-Alder reaction. Okay, but the question says that we're adding two equivalents of Lewis acid, so let's draw out another molecule of this Lewis acid, and imagine what might happen if we add in the second equivalent of Lewis acid. Well, we can imagine that through some means, this Lewis acid, the second equivalent of Lewis acid, could abstract this chloride anion from the first equivalent of the Lewis acid. Not too wild to think that may happen. There are no known mechanism. There's no known mechanism for this because we just simply do not know what happens during these kinds of reactions. But we can imagine that this chloride attacks the other chloride, and then this chloride leaves, and what you form would be if you assign new negative charges, like so. And then you would form a positive charge, so in the end, concentration of charges is conserved. But the mechanism of that is not important. The important point is that you need to realize how this second equivalent of Lewis acid actually can abstract a chloride from the first equivalent of Lewis acid. Right, so essentially we just created a positive charge on this aluminum, and we just said that Lewis acids do what they do because they lowered the LUMO of our system. Okay, so that means that this oxygen, which also has lone pairs, one of its lone pairs can also complex with this aluminum, because you just opened up a coordination site on that aluminum, right, by removing that chloride. So, I actually don't even need this. So this is what we are looking for. This would be this complex right here, right? It's just molecule B. And then this has to be our byproduct. And what's important to also note is that by complexing this second oxygen's lone pair, by coordinating the second oxygen's lone pair with the Lewis acidic aluminum, we're essentially locking the molecule in an cis conformation, so that this molecule won't twist around this bond, and as such, it would facilitate a faster Diels-Alder reaction.